let's talk about 3.1. This whole chapter is about graphs. Pretty much. It's all about graphing. Here's the goal. That's what we're doing. We're talking about graphs. That's the overall theme. The goal of this section, the why we're talking about it, is to get to the point where you guys can just look at something and go, ah, yeah, I see that now, without having to do a bunch of work. So often it happens, people type stuff into their calculator and they get a graph, and they go, oh, here's the graph of that, but they type something in wrong. And they don't realize that it's wrong because they don't understand what the graph should look like at the very beginning. If you had a simple equation like y equals 1 over x plus 2, and if you type that into the calculator, you know, it says y equals, and if you typed 1 and then did the divide symbol, which is going to be a little bar on the calculator, and then went x plus 2, that would give you a wrong answer. That would not be the graph. This is not the graph of that. They're different things. Because this is saying take 1 and divide it by the answer to x plus 2. And so in order to get that to work right on the calculator, you would have to put that in parentheses. Those would be totally different graphs. Similar-ish in appearance, but they're different. They'd be in different places. The goal of this is to be able to look at an equation and know what it's supposed to look like. We're trying to develop intuition. Be able to just go, aha, about stuff. Thank you. Aha, about stuff, without having to do the work. Now, the way you develop the intuition is to do some work. We're going to spend some time in Chapter 3 doing nuts and bolts kinds of things. But then the goal is that later on we won't have to do these things anymore. It'll just be very apparent to us. People who are good at math, and you're getting good at math, can just look at equations and understand and know things about them. That's our goal. But to get to that place, you got to do a little bit of nuts and bolts. That's what this is about. First section. Main theme in this first section has to do with symmetry. Symmetry is about balance. If you have any interest in architecture, you will be all about symmetry. You look at most homes, for example, they are symmetric. If you were to take a line, draw it straight down the middle of the house, things tend to be balanced. Now, there's also a lot of architectural stuff that's asymmetrical, where it's not the same on both sides, and they do that on purpose sometimes to break things up. But you look at a lot of houses, and there's a lot of symmetry to them. A lot of buildings are built that way on purpose. Your face is symmetrical. You have an ear on one side, an ear on the other side, an eye, and nostril here, nostril there, and you smile. And actually what this is about is really kind of an interesting thing. When one of the things I did, one of the degrees back over here is a psychology degree, and I did this degree in psychology, was going to pursue that, changed my mind. Anyway, I have this memory of, and I can't tell you what it was actually about in the psych book, but it was a picture, and it had 3 pictures. And the main picture was a picture of this man, and he had very distinct features, kind of meaty, an older man, kind of meaty face and big nose, and he was a nice looking man. It was fine. It was nothing. It was like your grandpa kind of a picture, right? But it was interesting, and the man was smiling. And then what they did is they took his face and they digitally divided it. They drew a line down the middle of it and looked at the symmetry of his face. They took the right side of his, or the left side of his face, and they double exposed it and flipped it over. And the way you smile, you think you smile kind of evenly, but it turned out it wasn't very even at all. And that one side was up a little higher than the other side. So they took the left side of his face and doubled it and made a new face with 2 left sides. And then they did the same thing with the right side of his face. They doubled it, flipped it over, and made a new picture with 2 right sides of his face. And one side kind of came out really kind of weird. I mean, the face looked fine as a normal face, but when you put the 2 right sides together, you got this really creepy, like I wouldn't want to be seen in a dark alley with this guy's face. And then the other side came out to be this real obnoxious, almost like Joker from Batman kind of face. It was the same face, but it was just, when you exaggerated that smile on one side, it just was really bizarre looking. Anyway, the point is symmetry, the balance. We are sort of symmetrical, but in some sense, we're really not too symmetrical. You know, you got a freckle over here that you don't have over there. You got a scar from something over here that you don't have over there, whatever. But you get the idea. We're going to look at these four main kinds of symmetry. Y-axis, origin, y equals x, and the x-axis. Graphs tend to be symmetrical with respect to, listen to how I say that, they are symmetrical with respect to these things. I'm symmetrical, more or less, with respect to a vertical line. Hand over here, ear over here, ear over here. I'm not symmetrical with respect to a horizontal line. Right? My face may look like my butt, but it's not. Again, it's not. You're supposed to go, thanks. So you have to be symmetrical with respect to something. Vertical line, yeah. Horizontal line, no. Top and bottom aren't the same. Left and right, yeah. They match up. So these are the things that we're going to look at. The book also does the line y equals negative x, and you might see that in some homework kinds of things. Don't worry about that part. It just doesn't come up very often. And here's what I'm talking about. Here's what it means to be symmetrical. I'm going to talk about the y-axis. If I have a graph that does something like this over here, and I know it's symmetric with respect to the y-axis, it's going to look like that over there. And what that means is, if I pick a point on one side over here, and I go straight across the y-axis, there should be another point just like it on the other side. That's what the symmetry means. Same distance over this way to this hand, same distance over this way to this hand. They match up across that line. If I did symmetry with respect to the origin, now that symmetry with respect to the origin is through a point instead of across a line. So if I pick some point and go straight through the origin, there's going to be that same point on the other side. Symmetry through the origin. And some graphs are symmetric with respect to the origin. And we're going to look at what kind they are. Now here's where this comes up later on in the mathematics. You're going to be dealing with some problems. Sometimes it comes up in calculus. And they talk about a function that's symmetric with respect to the origin, or a function that's symmetric with respect to the y-axis. And they're going to tell you all this stuff about the function that's going on over here. But then the question is going to be about something that's going on over there. On the left side, you're going to go, well, you didn't tell me anything about what's going on over there. But then you go back and you read it, it says, aha, symmetry with respect to fill in the blank. And then you're supposed to know, oh, if it was doing this over here, then it had to be doing this over here. And then you can figure out some stuff about what's happening down there. Just with that little piece of information. If I was talking about x-axis symmetry, if I could take the smartboard and fold it in half, yeah, things would match up. Pick any point over here, go straight through the x-axis, you should see another point just like it on the other side. That's what symmetry means. Now that's kind of the intuitive part. Now we're going to do the nuts and bolts parts. How do we get to that mathematically? How do I show, determine, figure out if something is symmetric? So let's start with something real simple. We're going to start with the y-axis. If I have some point, there's the point 4,2, and I reflect it over the y-axis. If I reflect it over the y-axis, it's going to end up over there. What's the only thing that changed about that point? The x. The y value stayed the same, right? Now, it may seem weird. I'm reflecting it over the y-axis, but the y value doesn't change. Just the x value. So on one side, you got positive x. On the other side, you got negative x. The only thing that changes in this situation is that x value. It goes from positive to negative. And so that's what you end up doing when you have an equation. You get symmetry on some equations across the across the y-axis, and whether you put in positive x or negative x, you get the same answer. For example, look at x squared. Back in Algebra 1, you guys learned about graphing parabolas. You maybe, I forget my next slide, yeah. So look what I do. I picked a number for x, and I can put it into the equation. I'll get some answer. But if I put the opposite of x in, you're going to get the same answer. Because look what happens when I take negative x and I square it. Negative x times negative x is positive x squared. If you can put in the opposite of x, that's what I did here. I put in the opposite of x. If you can put in the opposite of x into an equation and get the same answer as what you started with, then there's symmetry across the y-axis. That particular one is so special it has a name. We call it an even function. If a graph is symmetric with respect to the y-axis, it's an even function. There's only two of them that have names. This is one of them. So symmetry across the y-axis is an even function. So like I said, I've seen it happen in a calculus where they say, there's an even function such that blah, 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 blah. And they tell you all this stuff about even functions. And it's all about what's going on the right-hand side. And then the question is about what's on the left-hand side. You go, well, you didn't tell me about the left-hand side. And then you go, oh, yeah, even function. And now that means everything that they told me about what's going on over here tells me about what's going on over here because I know the symmetry. Even function. How do you check for symmetry with respect to the y-axis? Take out the x. Take out the x and replace the x with the opposite of x. So I took out the x in this problem, and I put in the opposite of x, and I got the same thing. And if I get the same thing that I started with, it's symmetric. Look at it on the picture. Whether I put in x or I put in negative x, I'm going to get the same answer. Deep breath there. Another way of doing this, there's two ways of kind of thinking about this with an even function. If f of x is equal to f of negative x, that's doing the same idea as just using function notation. If f of x is equal to f of negative x, then it's an even function. It's symmetric with respect to the y-axis. Here's a question for sure I will give you. Sure. Okay. All right. Just almost exactly like this. I'll give you some function. And say, is this an even function? Or show that it's even, or show that it's odd. Function. So, question here, show it's even. All right, so what we just had was, if it's an even function, these two things should be equal to each other. So I'm going to find those two things. Well, I already got f of x. There's f of x. What I now need to find is what's f of negative x. So I'm going to take out, look what I've done. I simply take out the x, and I replace it with negative x. Well, negative x squared is positive x squared. And negative x to the fourth power, negative x times negative x times negative x times negative x, 4 of them, right?
Please excuse the interruption. At this time, would all freshmen with last names A through C please report to C20?
So when I did this, I ended up, when I plugged in negative x, I ended up getting this answer. Now look back in your notes there a couple of steps. It says if f of x is the same thing as f of negative x, are these two lines exactly the same? Is this one exactly the same as that one? And it is. And so what you've shown, what you've proven, is that this function is symmetric with respect to the y-axis. it's an even function. The answer is yes or no. Well, the question was, is it even? Yes. I'm not going to give you credit for just answering yes or no. You need to support your answer with something. What supports this answer is your demonstration to me that this is equal to that. That's the support for the problem. Is f of x equal to f of negative x? If I say, well, how do you know? You tell me this, because f of x is equal to f of negative x. Whether I go this way or whether I go this way, I get the same answer. That's symmetry. Is this one even? Well, looking at the picture, is there symmetry across the y-axis? Head's shaking back and forth. No, there's no symmetry here across the y-axis. If I pick a point and go straight across the y-axis, there should be a point just like it on the other side. There's not. This graph's not an even function. Now, if you're starting to pick up on the idea, there's a direct relationship to the power and whether or not it's an even function. If it's raised to the third power, fifth power, seventh power, it's not going to be an even function. Just because it's raised to the second power doesn't mean it's an even function, but that's a good start. So no, this guy's not symmetric with respect to the y-axis, no symmetry. And I think I do it here, no. So let's say I wanted to prove it. I can look at the picture and know for sure, but here's what I want to show. Let's take a look at what f of x is. Looks like this. Now I'm going to put into the equation negative x. So f of negative x is equal to, well, now I got negative x times negative x times negative x. And the answer is negative x cubed. Yep. So is f of negative x equal to f of x? Are these two things the same? No. Now I'm picking really easy problems, but that's the essence of what's going on. That's what you have to be able to show. That's the mathematical support of what you're seeing in that picture. No symmetry across the y-axis. Symmetry with respect to the origin is the other one that has a name. Symmetry with respect to the origin, this is 2. Symmetry with respect to the origin is an odd function. Those are the two that have names. Y-axis symmetry, even. Origin symmetry, odd. One of the big things that we're going to deal with later on this year is in the trigonometry. Second semester, we're going to spend a lot of time doing trig. The sine, you've done trig back starting in Algebra 1. You did real basic trig back in Algebra 1. The sine function is an odd function. The cosine function is an even function. There's symmetry with respect to the y-axis for the cosine, symmetry with respect to the origin for the sine. Knowing that about those curves tells you a whole bunch of stuff mathematically. So let me go back to this one. Let me plug in the negative x again. It's the same one we just did, right? Plug in negative x. When I plug in negative x, I get negative x cubed. F of x doesn't equal f of negative x. So it's not an even function, right? We already figured that out. But look what happens when you do symmetry with respect to the origin. Pick some point. Remember that point 4,2 I had? If I go straight through the origin and come down to the other side, I end up with the point, negative 4, negative 2. What happened to the coordinates of 4, 2? What happened to these guys? Second? They both become the opposite. It's negative 4 and negative 2. Look, when I take the point negative 1, 2, and I go straight through the origin, it becomes positive 1, negative 2. It's the opposite of both of them. So it's not, remember with the y-axis, it was just the x value went backwards, went negative. Now it's both of them have to go negative. Both of them have to go negative. You have to take the opposite of both x and y when you check for the origin. the opposite of both the x value and the y value when you do the origin. All right, so how's that play out in a problem? Well, if I wanted to check this one for symmetry with respect to the origin, take the x value out, take the y value out, replace them with the opposites. Replace them with the opposite of the x and the opposite of the y. And just like we did with the y-axis symmetry, if I replace this, right here I got negative x, negative y going in, if I replace that, and I can solve the equation, simplify the equation, rearrange the equation, and make it exactly the same as what I started with, these two guys are equal to each other. I put in the opposite of x, I put in the opposite of y, and I got the exact same thing I started with. If you can do that, ding, 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 and you have to make that sound when it happens, there's symmetry with respect to the origin. If it's a function, you can say it's an odd function. That's the only vocabulary, the only two that have names, even and odd. So the graph y equals x cubed is an odd function. It's symmetric with respect to the origin, because after I put in negative x and negative y, I got exactly what I started with. Let's check for symmetry. Remember how odd functions, there's a relationship I said between the exponents? Huh, look at that. 3 is an odd number. Let's check this guy. Kind of looks like maybe it could be. Let's see. I want to check symmetry with respect to the origin. If it's symmetric, some fun thing should happen. I should be able to take out the x, and I should be able to replace that x with the opposite of x. And I should take out the y, and I should place the y with the opposite of y. If that's true, if it's symmetric with respect to the origin, doing that should get me the exact same equation I started with. So let me simplify a little bit. Negative y comes down. Negative x cubed is negative x cubed. Times 2 is negative 2x cubed. Negative negative x is positive x. Plus 1 plus 1. If you can solve, rearrange, do whatever you need to do to get this, try to make this look like what I started with. The original one said y equals, so I decided to divide through by negative 1. So is the new thing the exact same thing as what I started with? No. Therefore, you got no symmetry. It's daggone close, isn't it? But it's not the same. Since those two things aren't the same thing, this graph is not symmetric with respect to the origin. And the thing that made it a problem was this plus 1 at the end. The rest of it's the same, isn't it? So if there hadn't been that plus 1, this graph would have been symmetric with respect to the origin. The plus 1 did something to the graph. One of the things we're going to talk about this chapter is being able to look at that and understand what the individual numbers do to an equation. What does that plus 1 do to the graph? Let me take a deep breath there. Question about some piece of what you see there. Yeah.
So, the last line you have written, did you just take the opposite of the line?
Right. I just divided through by this because of the negative right here with the y.
Oh,
I just divided through by negative 1 everywhere to make it a positive y.
Okay.
And because I was trying to make it look like this guy at the beginning, and the guy at the beginning here was a positive y, so let me make this a positive y. But then when I did that, this is not the same. And the whole equation's got to be exactly the same, otherwise it doesn't work. Another way of thinking about this, the even and odd both have two ways of thinking about this. Even and odd are special unique situations. If it is a function, and not everything is a function, but if it is a function, this should be true. If it's a function, that should be true. That f of negative x should be equal to negative f of x. Looks an awful lot like the even one, right? The even one, though, this was a positive in there. No, that's not true. Let me try that again.
Please excuse the interruption. Will all freshmen with last names starting with D and E please report to C20? Please line up outside the room. Thank you.
This is what the even one was. But the odd one is this. The even one said if you can put in negative x and get what you started with, it was even. But this guy, it's the opposite of it. So this is like negative x right here. But remember, f of x means y. F of x means the y value. And so that's what you're doing here is you're taking the opposite of the y and you're taking the opposite of the x. That's an odd function. You're taking the opposite of both. So if I said, is something an odd function? That's what you want to show. Show that f of negative x and negative f of x are the same thing somehow. So, for example, let's try. Show that it's an odd function. I'll give you a 10-second head start here. If it's an odd function, you should be able to show that that's true. If it's an odd function, show that that's true. So find f of negative x and find negative f of x. And compare them. So let me start off by finding this guy first. So take out the x, and everywhere you see an x, put in negative x. Get an answer. So that's f of negative x. Tuck that aside somewhere on your paper. Then I'm going to find negative f of x. That's the other side of the equation, right? Hey, looky there. What do you see? They're the same. It's the same thing. So what I've just shown mathematically, because I've shown that f of negative x and negative f of x are the same thing over here, since those guys are the same, I've just shown that this is an odd function. This function, when you graph this on your calculator, it should look like it has symmetry through the origin. So dig out your machine for a second, graph this original equation, and let's take a look at what it looks like. Check to see if this is even or odd. No. Do it mathematically. Check even or odd.
Please excuse the interruption.
This is what I need to see. I need to see if these two things are equal to each other. That's what makes a function an odd function. If those two guys are equal to each other, it's an odd function. There's symmetry through the origin. And again, our goal here is to get to the point where we can just go, oh yeah, I can tell you something about that. I know what this graph's supposed to look like. I can draw this graph real quickly without touching the calculator. A, because I've spent a long time doing it, but I know things about symmetry. So to plug in negative x. When I plug negative x in, everywhere there's an x, I end up with this. When I take the opposite of the function, It means take the opposite of everybody. And I end up with this guy. So is f of negative x equal to negative, set it backwards, is f of negative x equal to negative f of x? Are those two things the same? No. Therefore, you got no symmetry. It is through the origin. It's not an odd function. Once you get here, if these two things were the same, it's an even function. Are these two guys the same? Is that guy the same as that guy? It's not. Because you got positive x cubed minus 1, and the other one's negative x cubed minus 1. They're not the same. You got no symmetry. Roman numeral 3. Yes, sir. Kind of like this, yeah. With the origin, it's both of them are negative. With the other one, it's just the x value is negative. This is, in this particular chapter, or this particular section, not a really huge deal. But in a couple of sections, we're going to do some things with inverses of functions. And in that situation, this is a much bigger deal. There are not a lot of graphs that are symmetric with respect to the line y equals x. Very, very few actual graphs. But the symmetry across that line is a big deal. All right, so first of all, remember back to my point. Actually, I think I had 4,2 before. Anyway, but if I got this point at 4,1, and I do symmetry across the line y equals x. Y equals x, remember, is just y-intercept of 0 and a slope of 1. That's y equals x. But if I can find symmetry across that line, if I go straight across this line, look at what happens to the coordinates of those points. For both positive, in this case, you just simply, flip them around. So no matter what point I have, if I were to go 1, 2, 3, 4, 5, negative 3. Here's the point 5, negative 3. So if I go straight across this line, what I'm going to end up with is that what I just said? Yeah, this is 5, negative 3. Where I'm going to end up with 1, 2, 3, 1, 2, 3, 4 up here, at negative 3, 5. So straight across that way would be a point that matches it. That's symmetry across the line. Again, of the line y equals x. Again, look what you're doing. What's happening is the x and the y values get flip-flopped. You interchange the x and the y. To check for symmetry over the line y equals x, interchange the x and the y. One of the things I'll do off and on this year is to give you suggestions about something that I think could be helpful to you during the course of your math stuff. This year, we're going to pick up tons of just little stuff like that idea. How do you check symmetry across the line y equals x? Interchange the x and the y. What I would strongly encourage you to do is to make flashcards with just little stuff like that. None of it's hard. That's not a hard concept. It's just that there's 1,001 little things. And if you would regularly add, a couple things to a little stack of flashcards now and again, it's not going to be the overwhelming mass of information that it is when you wait till the end. Start it now. Make a little stack of them. Just add something real simple. These little simple ideas. How do you check symmetry across y equals? That's what it would say on one side. I'm sorry, the y-axis. It would say on the other side, it would say put in negative x. Put in the opposite of x. How do you check symmetry across the line y equals x? Interchange the x and the y. They're not hard ideas, but it's just that there's a lot of them. And you got to be able to just, oh yeah, that's what you do. So, visually, what a graph looks like that's been reflected over the line y equals x. This graph is not symmetric with respect to the line y equals x, pick some point, go across here. There's not a point like it on the other side. So this parabola is not symmetric with respect to that line. But there will be some times where we want to reflect a graph over that line. And so what that means is you start picking points and go straight across and plot them. So pick some point here, go straight across and plot it. So that should be a point straight across. And if I do enough of those, by the way, if I'm right on the line, it doesn't go anywhere. So that point doesn't go anywhere. This point doesn't go anywhere. Go straight across. And if you do enough of those, you'd get something that looks like that. Now, like I said, there are very few graphs that are symmetric with respect to the line y equals x. There are some, but not many. But what we will do mostly with this is, instead of having a graph that's symmetric, is we will reflect a graph across that line and create a new picture. So the right side up parabola becomes the sideways parabola, which is, of course, is the logo for the University of Cincinnati. You listen next time they do their cheer, you know, they do that thing and they go thing and they go and then they go clap, 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 and you think they're saying, you see. That's not what they're saying. They say, what they're really saying is, reflect over y equals x. You listen really carefully, that's what they're saying. Okay, sorry. So this is what's going on. If these two graphs are symmetric with respect to the line y equals x, I should be able to interchange the x and the y and get the same thing I started with. Well, look, is this equation down here the same thing as what I started with? No. And so the original graph is not, it's not symmetric over the line y equals x. Is this a graph of something that's symmetric over the line y equals x? Yeah. Let me back up for a second. So what I was trying to show there, Kendall, is that this graph is not symmetric with respect to the line y equals x. The original right side up parabola is not symmetric. And when I interchange the x and the y, I put the x value over where the y value was, and I put the y value in where the x value was. And when I tried to solve for y again, it did not give me the same thing I started with. So no symmetry. Just like we were doing with the other stuff. Is this a function? Is this the graph of a function? No. Is every member of the domain paired with only one member of the range? Here's an x value. Oh, look, there's a y value that matches up with it. There's a y value that matches up with it. So this is not a function. Is it symmetric with respect to the line y equals x? Well, here's the equation. That's the equation, of course, of a circle. The center is at the origin. What's the 9 telling you? How wide it is. What's that called in a circle? Radius. It's the radius, and the radius is 3. It's x squared plus y squared equals r squared. Back to your geometry days. X squared plus y squared equals r squared. The radius is 3. So it's symmetric, but it's not a function. If I wanted to show, verify, indicate, whatever, that it is symmetric with respect to that line, I should be able to interchange the x and the y. I'm going to take out the x and replace it with y, and I'm going to take out the y and replace it with x. And when I did that, by golly, that's the same thing as what I started with. It's in reverse order, but that's the same thing, right? 2 plus 3 and 3 plus 2, it doesn't matter how you add things up, it's the same thing. So if I go y squared plus x squared, that's the same thing as x squared plus y squared. What I've just done is shown, proven, verified, pick your word, that this equation is symmetric with respect to the line y equals x. Oh, by the way, that circle is symmetric with respect to everything we've just talked about. If I can take out if I wanted to show symmetry across the y-axis, you change the x to the opposite of x, and you leave the y alone. Is that the same is what I started with. Heads nodding up and down. Yippers. I started with x squared plus y squared equals 9. That's where I ended up. If I wanted to check symmetry through the origin, I take both the x and the y and change them into the opposite. And so simplifying this guy, I get that. Simplifying this, I still get that. There's symmetry through the origin as well. Last one, x-axis. Yes, sir. Sure. There we go. Kind of a process of elimination. And visually, look what happens, right? When you go across the x-axis, the only thing that changed was the y value. Perfect. And you're going to do the exact same logic that we just talked about. If I can take the equation, replace the y value with the opposite of y, then it's a function. Then it's symmetric, not a function. X-axis symmetry, by the way, cannot be a function ever. Because if there's a point above and a point below, remember that vertical line test, what that's showing? It's not a function. So, for example, look at this equation. And this is an old Algebra 1 thing that maybe you, or maybe geometry, I don't know. But if you take and take out the y, this is the equation x equals y squared. That's what a sideways parabola is. And if I put in the opposite of y, and I get what I started with, since those guys are the same, I got what I started with, putting in the opposite of y, therefore there's symmetry over the x-axis. Yes. Ish. Thing. It's a sideways parabola, though. All right, in a nutshell, real fast. If I have some function, and this will be sometimes a question I'll give on a test or quiz too, and I'll give you a piece of a function.
Interruption. Will freshmen with last names J, K, and L, that's J, K, and L, please report to C20 for hearing and vision screening and line up outside the door. Thank you.
I'll give you a function. I'll say, here's part of a graph. Find for me what the graph would look like if it was symmetric with respect to each of these. So if this was part of a graph and it was an even function, even functions have symmetry over that line. And so this is what the rest of it would look like. So I'll give you just the right-hand side and say, what's the rest of the graph look like if it's even? Well, even, symmetry over the y-axis, it'd have to look like that. If it was odd, it's symmetry through the origin. So when this one goes up, over, and then up again, so this is going to go down, over, and then down again. That's what the odd one would look like. If I said x-axis, it should look like that. Let me go through those again. I know I was going a little fast there. Even one should look like that. An odd one would look like that, symmetry through the origin. The x-axis would do that. And the line y equals x would do that. It's sometimes nice to kind of draw this line in to get a feel for where it is. So it's evenly balanced right across that line. That's it. Yeah. Yeah, let me see one thing real fast here. So, tomorrow I won't see most of you, so you got a little bit of time in order to do this, but we'll do homework out of 3.1. They will also do the line y equals negative x. Take a look at that one. If you figure that one out on your own, that's fine. I probably won't ask you about that one, though, at all. Kendall, which one did you say?
The line one.